So now that we know that our model diagnostics are looking good and we're able to proceed, let's run the summary function on our model, barm.mod. The summary function, again, starts off with the specification for the linear model that we built, the arguments that we fed it, a breakdown of the different residuals, and their quantiles, and then from the coefficients on down, that's really what we care most about. So you'll see here that there are 3 different rows in the coefficient section. There's one for intercept, one for flake axes, and one for denticulated or notched pieces. As you'll recall from the previous video tutorial, what R does when you're dealing with a categorical predictor variable is it assigns the first group, the first category, to the intercept. So in this case, when we are looking at this kind of model output, microburins has been assigned to the intercept. And so the estimate here for the intercept is the same as the estimate for the mean Easting value of microburins. And then we've got the coefficients for flake axes and denticulated and notched pieces. Now, as before, right, we can calculate the estimated means for all of these. This isn't something that you necessarily are always interested in, but it's important to understand how this works so you can better understand what the model is actually doing. So let's just work through this once again so you can see how the model is being built. So we're going to use the with function here, and I'm going to say with barm data, and specifically index the barm data so that we're looking at just the microburins. Put a comma there, and then another comma outside of the brackets, and then I'm going to say mean East. So what this function that I just wrote is doing is saying, okay, with the barm data, and specifically with the microburins from the barm data, because I'm indexing barm data by the microburins, with that data frame that I've got highlighted here, calculate the mean East value. If you run this, the answer is 6.336. You'll see that is the same as the intercept estimate, 6.336. That's because we're looking at just the first group, microburins, which is the intercept. And so when you think about our equation that we've got, where whatever it is we're trying to predict, and we've got beta 0 plus beta 1 times x, and now in this case we've got another term, beta 2 times x. Each of these beta values is one of our groups. And we've got 3 different artifact types that we're looking at here. The intercept is always there. That's 6.336. And in this case, let's call these x1 and x2. We are not adding either of the beta values because we're not interested in flake axes or denticulated notched pieces. So these become 0. So our calculation for this is the intercept, 6.3363, plus the coefficient for flake axes times 0. So if you multiply that times 0, it cancels it out, right? And then we're also adding the coefficient for the dn pieces, but also multiplying that times 0 because we're not concerned with that. So this is the model equation that we're using to calculate the mean estimated Easting value for our first category, microburins. Right? And so if we run that, again, it's the same, 6.336. If we wanted to calculate the mean Easting coordinates, or the mean Easting coordinate for flake axes, that is our second group here, right? So we need then this coefficient estimate, negative 0.9238. So in this case, you still need to account for the intercept. You're always adding your intercept in. Whereas before, the mean Easting coordinate is the intercept because we're not adding anything else because we multiply everything else times 0. In this case, we're not multiplying everything else times 0. Going back up here, this now becomes a 1 because we're multiplying this value times 1, so we're including it. We're still multiplying the coefficient for denticulated and notched pieces times 0 because we're not concerned about that. And so now it's 6.336 plus negative 0.923. So it's effectively 6.33 minus 0.923. If we run this, we get a value of 5.4125. That's going to be the mean Easting coordinate for flake axes. And if we copy this code over and run it on flake axes, so with this data frame, just the flake axes from BARM data, run the mean of the east, run the mean function on the east column. If I run that, same answer, 5.4125. Right, that's what that's reflecting. And finally, if we look then at the denticulated notched pieces, and we're interested in that, the coefficient, or rather the x value that we're multiplying by the second coefficient, that returns to 0 again, because we're not looking at flake axes, we're just looking at DN pieces. So the third one becomes a 1. And so we multiply 0.4472 times 1, we add it to the intercept, and of course we're also adding it to the second one, but not really because that's times 0. So it's really just adding this to this. We do that, and we get a value of 6.7835. And again, if we were to copy down this code to calculate that, and instead of flake axes, put denticulated / notched pieces, run that, same answer, 6.7835. So this equation here, right, all we're doing now is instead of having just 2 beta values like we did in the previous tutorial, we've now added a third beta value, beta 2, beta naught, beta 1, and beta 2, representing our 3 different artifact types. If you were to make a model like this with 10 different artifact types, you would have 10 different beta values here. This is what I mean by an additive linear model. You just keep adding these terms onto each other. That's one of the main assumptions of a linear model, is that you can do this. And it makes the math really easy to predict these values, as you've seen. If you're not concerned with that category, you multiply that coefficient by 0. If you are concerned with that category, you multiply it by a 1. Add all of that together with the intercept always included, and you can estimate the mean value of the response variable that you're interested in.